All right, so you've sent over a whole, like, mountain of information here. Speech and language processing, huh? Looks like we're going deep, deep down the rabbit hole with these excerpts from speech and language processing. It's a textbook, right? Still in progress.
Yeah, it's a work in progress. But what's really cool about this field, I think, is how it blends linguistics with computer science. Even a little psychology sprinkled in there. It's not just about making computers, talk like us. It's about understanding the very nature of language. Like, what is language?
You know, I love those light bulb moments, those aha moments. And just glancing at this stuff, I can already tell this deep dive is going to be chock full of them. We're talking about how machines learn to, like, decode human language, predict what we're going to say next, even synthesize speech that sounds, well, kind of creepy how real it's getting. Okay, so first things first. Let's hit rewind for a second, look at the history of this whole thing. What were some of the early wins and what shifted everything towards this data-driven approach everyone's using now?
Well, the early days were super influenced by Noam Chomsky. Lots of focus on rule-based systems. It's almost like trying to program every single grammar rule into a computer manually.
Hmm.
But the more people dug in, the more they realized natural language, way, way too complex for that. So many nuances, exceptions, you can't just pin it down with hard and fast
Well,
rules.
hey, language is always evolving, right?
Uh,
Changing all the time. So what changed the game?
Machine learning came along, and suddenly we had access to these massive data sets. Things like the Penn Tree Bank, which is this huge collection of text that's been tagged with all the syntactic structures. That opened up a whole new world. We could train algorithms on real, actual language, let them find the patterns, make predictions based on statistics.
So instead of force-feeding computers all these rules, we started showing them examples and letting them learn from that.
Exactly. And that turned out to be way more effective, especially for tasks like part of speech tagging and parsing, where you're trying to break down the grammar of a sentence. And with the explosion of digital text, that trend has just kept getting stronger.
Wow, that's fascinating. Feels like this machine learning thing really like democratized the field. Suddenly you could tackle problems that were totally impossible before. But before we get ahead of ourselves, let's talk about some of the fundamental tools. Regular expressions and automata sounds kind of sci-fi, doesn't it?
Uh-huh. Yeah, a bit. But they're actually pretty elegant when you get down to it.
Yeah.
Regular expressions, we call them REs for short, are basically a way to describe patterns in text. Think of them as like superpowered search tools. They can find specific words, sure, but also these crazy complex combos of characters.
So, like, if I wanted to find all the times we say deep in this deep dive transcript, I can use a regular expression for that.
You got it. But REs go way beyond that. They use special symbols, operators, to build these intricate patterns. You can hunt for phone numbers, email addresses, even grammatical structures within sentences.
Okay, starting to see how powerful these REs can be. But what about these automata? Where do they fit in?
Think of automata as these tiny little machines designed to recognize the patterns you describe with regular expressions. A finite state automaton, or FSA, is a basic model of computation, limited number of states and transitions between them. Each state is like a different point in analyzing a string, and the transitions tell the machine how to move from one state to the next, depending on what it sees in the input.
So if you feed an FSA a chunk of text, it can tell you if it matches a specific pattern, right? Yes or no?
Yep, exactly. Like having a tiny robot scanning the text, giving you a thumbs up or thumbs down based on whether it finds what it's looking for. And the cool thing is, these FSAs can model anything from simple word sequences to complex grammar structures.
This is starting to make sense now. Pretty amazing how these abstract ideas have such real-world applications in language processing. But let's zoom in on words for a second. How do we break them down into the smallest pieces that still have meaning? I'm guessing there's a whole science behind that.
You're talking about morphology, the study of how words are formed. And you're right, it's a whole fascinating area. In English, we've got two main types, inflectional and derivational. Inflectional morphology is about changes to a word that don't really change the core meaning, like adding s for plurals or ed for past tense.
So cat becomes cats and walk becomes walked. Simple enough, right?
For the most part, yeah. But, English loves to throw goofballs. We've got those irregular forms that always mess things up. But derivational morphology, that's where things get really juicy. That's when you add prefixes or suffixes to create new words with completely different meanings, like adding un to happy to get unhappy, or pumpsly to quick to get quickly.
Ah, so we're not just tweaking the tense or the number, we're actually changing the meaning of the word itself. But how on earth do we teach a computer to understand these subtle transformations, especially with all the crazy irregular forms and exceptions in English?
That's the million-dollar question. One way is to use finite state transducers, or FSTs. They're like FSAs on steroids. They can recognize patterns, but they can also transform them. So we can use them to model how prefixes and suffixes are added, taking into account all those quirky English rules and exceptions.
So it's like giving our little robot a blueprint for building and modifying words, like a miniature word factory.
Exactly. But even with FSTs, modeling English derivational morphology is a headache. The rules are fuzzy, tons of exceptions that don't fit neatly into categories. Take clear, for example, becomes unclear and clearly. But then you have adjectives like big that can only take one of those suffixes, not both.
Yeah, language is messy like that, always breaking the rules we try to impose on it. So what do researchers do? Just give up?
Not quite. They've come up with some pretty clever workarounds. One approach is to create these, like, fragments of FSAs. They're based on tons of research and analysis of huge amounts of text, capturing the most common patterns of word formation. Then they can use those fragments to analyze new words and make educated guesses about their structure.
So it's like putting together a giant linguistic jigsaw puzzle, using fragments of knowledge to fill in the gaps.
That's a great way to put it. And to make things even more complicated, even just splitting text into individual words can be tricky.
Wait, really? I thought it was pretty obvious where one word ends and the next one begins.
To us, maybe. But computers, they don't have that same intuition about language. Like, is New York one word or two? What about contractions like can't? Or hyphenated words like state of the art? These are the kinds of questions that come up when you're developing algorithms for word tokenization. That's the process of segmenting text into individual words.
Ah, I see. So even something as basic as splitting text into words can turn into this complex computational problem. But do researchers have to, like, program computers to understand every single rule and exception?
Well, thankfully, no. There are more efficient ways to do it. One common approach is to combine regular expressions with dictionaries. Regular expressions can identify those patterns that usually signal word boundaries, like spaces, punctuation, changes in capitalization.
So, like, if a computer sees a space, it can assume that's the end of one word and the beginning of another.
Most of the time, yeah. But of course, there are exceptions. That's where the dictionaries come in. By including a list of common abbreviations, contractions, all those special cases, we can help the computer avoid making the wrong splits.
Sounds like a constant balancing act between general rules and very specific exceptions.
It definitely is. And this is just scratching the surface of the challenges in natural language processing. But even with all this complexity, researchers have made incredible progress. We've got algorithms now that can analyze and manipulate language with pretty impressive accuracy.
And I can't wait to hear more about those advancements. But I think this is a good spot to take a break. We've covered a lot, from the history of speech and language processing to the nitty-gritty of breaking down words.
Yeah, we've laid a good foundation. Looking forward to diving into even more fascinating stuff when we come back.
Okay, welcome back to our deep dive into all things speech and language processing. We've been looking at these building blocks of language, breaking down words, sentences, all that. But now I want to see how we can actually use this stuff to build systems that, actually get human language.
Absolutely. And one of the key steps there is part of speech tagging. We call it POS tagging for short. Might sound simple, but it's actually fundamental in NLP. Basically, you're labeling each word in a sentence with its grammatical category, noun, verb, adjective, all that.
So, like, if we had the sentence, the computer processed the language, we'd tag computer as a noun, processed as a verb, language as a noun again.
Right on. But as easy as it is for us, getting a computer to do this accurately, that takes some serious understanding of grammar and how language can be, kind of slippery.
Yeah, for sure. Words can play different roles depending on the context. So how do we, teach a computer to deal with that ambiguity?
Good question. One way is to use rule-based taggers. These systems, they rely on handcrafted rules that basically tell the computer, okay, if a word ends in "eng," it's probably a verb, kind of thing, based on the word itself and the words around it.
So going back to our example, a rule might say, if a word ends in "ing," it's probably a verb. So the tagger would use that to tag processing as a verb.
Exactly. But can you imagine trying to write down every single rule for English? It'd be a nightmare. Just way too many possibilities.
Totally. So what's the alternative if rules aren't enough?
Statistical taggers. specifically ones that use hidden Markov models, or HMMs. Remember, we were talking about n-gram models and how they predict word sequences. HMM taggers are similar, but instead of predicting the word, they predict the tag.
Okay, so an HMM tagger looks at a whole sentence and then tries to guess the most likely sequence of tags based on patterns it's learned from, like a ton of text.
You got it. And we can train these models on massive data sets of text that humans have already tagged. So the algorithm have a bunch of correct answers to learn from.
Ah, so the model learns from these examples and then uses that knowledge to make predictions about new text it's never seen before.
The heart of machine learning. And just like with n-gram models, there are all these techniques to make them more accurate. Smoothing to deal with new words, adding extra features like capitalization, punctuation, give the tagger more clues to work with.
So it's like we're giving the tagger a whole toolbox to help it figure things out.
Exactly. And as the field has evolved, researchers have built even more sophisticated taggers, using things like maximum entropy models, decision trees, even deep learning, getting some really impressive results.
This is amazing. Feels like these taggers are becoming real grammar experts. But I'm thinking about those closed class words we talked about earlier, the super common ones like the, a, and, of. They seem like they could really trip these taggers up.
You're telling me closed class words or function words, they're a major pain for POS tagging because they can have so many different roles depending on where they are in a sentence. Like take can, for example, can be a noun, like a can of soda, or a verb, I can code.
Yeah, that's true. So how do taggers handle that? Do they just kind of guess based on the other words around it?
Context is super important, yeah. But they also use what they know about word frequency, probability. Remember those different tag sets we talked about, like the Penn Tree Bank tag set with its, 45 different tags? That helps standardize how we label words.
Right, right. So if the tagger sees can, and it knows that statistically can is used more as a verb than a noun, it can make a more informed guess, right?
Exactly. Yeah. Doesn't always work perfectly, though. Sometimes word frequency and probability just aren't enough to figure out those really ambiguous cases. That's when you need to bring in the heavy hitters. Analyzing the sentence structure or using fancier machine learning models that can pick up on those more complex relationships between words and tags.
It's like a constant battle between ambiguity and, like, trying to be super precise.
It is. That's what makes NLP so challenging,
Yeah.
but also so rewarding when you get it right. And despite all that complexity, research has made some crazy progress. Some POS taggers are getting accuracy rates of over 97%.
Wow, that's incredible. Feels like we're getting closer and closer to human-level understanding of grammar. But before we go too far down that road, how did we even get to this point? What were the big breakthroughs that led to these super accurate taggers?
Oh man, the history of POS tagging is a story in itself. Early taggers back in the 60s were all about rules and dictionaries, handcrafted stuff, really limited, and they struggled with all the ambiguity in language.
Yeah, I can imagine. Programming every rule of English grammar into a computer sounds like a total nightmare.
It was. But those early attempts, they were important. They paved the way for the statistical taggers that came along in the 80s and 90s. Hidden Markov models came on the scene, and then we had these big annotated data sets like the Penn Tree Bank. Total game changer.
So we went from trying to teach computers all the rules to showing them examples and letting them learn the patterns themselves.
Exactly. And this empirical approach, it just worked better, especially as computers got faster and we had better algorithms for training HMMs on huge amounts of data.
So it was like the right tools, the right data, all coming together at the right time.
Yep, perfect storm. And it didn't stop there. Machine learning techniques like maximum entropy models, transformation-based learning, that's TBL, all these things kept pushing the accuracy higher.
I'm seeing a pattern here. Every time we hit a roadblock in language processing, somebody comes up with this clever algorithm or technique that pushes the boundaries even further.
That's what keeps this field so exciting. Always evolving, always finding new ways to tackle these challenges. And like we saw with POS tagging, even these seemingly simple tasks, they need a deep understanding of linguistics, statistics, computer science, all of it.
Couldn't agree more. And this whole journey of innovation, it's not over yet. I'm really curious to see where POS tagging goes next, what people come up with. But before we get ahead of ourselves, let's dig a little deeper into these techniques for boosting accuracy. You mentioned things like word context, orthography, morphology. What does all that mean?
Right, so modern POS taggers, they're incredibly sophisticated. They look at way more than just the word itself. For example, they can consider the words that come before and after the target word. That gives them valuable clues about the context.
So if the tagger sees duck and it knows the word before is a, it can figure out duck is probably a noun, like a duck, not a verb, like duck for cover.
Exactly. They can also analyze the orthography, that's the spelling and punctuation. A word starting with a capital letter is more likely to be a proper noun. A word ending in "brannily" is often an adverb.
So these features are like little hints helping the tagger navigate through the sentence and make better choices.
Love the analogy.
Yeah.
And we can go even deeper, incorporating morphological features, like the words stem, prefixes, suffixes. For example, the tagger might see unbreakable and break it down, prefix un, stem break, suffix able. And from that, it can figure out, okay, this is probably an adjective.
It's like we're giving the tagger X-ray vision.
Hey,
It can see inside the word and understand it on a deeper level.
that's a good one. And we can combine all these features in different ways.
Hmm.
Machine learning algorithms can figure out the best way to weight them, how they interact. That leads to even more accurate and robust taggers.
Truly remarkable. We're teaching computers to analyze language with, like, crazy precision, almost like they're understanding it the way humans do. But hold on, you mentioned earlier that some of these advanced taggers can get accuracy rates above 97%. That's insane. But how do we actually measure that accuracy? What's the benchmark?
The standard way is to compare the tagger's output to a gold standard. That's basically a manually annotated corpus of text. It's like the ultimate truth. So for example, we often use the Wall Street Journal, part of the Penn Tree Bank. It's a common benchmark for taggers trained on English text.
Okay, so we basically give the tagger this benchmark text, compare its tagging to what the humans did, and see how well it does.
You got it. And we can use a bunch of different metrics to measure the agreement between the tagger and the gold standard. Accuracy, precision, recall, F1 score, all sorts of stuff.
So if a tagger says it has 97% accuracy on the Pentry Bank, that means it tagged 97% of the words correctly in that whole massive data set.
Exactly. And that level of accuracy, it really shows how powerful machine learning is and how much work researchers have put into these algorithms.
It's mind-blowing. Makes you wonder, are there any limits to what we can do with POS tagging? Is there a point where it's just, like, good enough and it doesn't really matter if it gets any better?
That's a good question. Even though we've come so far, there's always room for improvement. One area that's really hot right now is unsupervised tagging. That's where the tagger learns to assign tags without needing a manually annotated corpus.
So instead of us giving the tagger all the right answers, we just give it a ton of text and let it figure things out on its own.
Exactly. It's way harder, of course, but it has huge potential. Could help us discover new things about how language works and tag text in languages where we don't have much annotated data.
Really interesting stuff. Feels like we're always trying to make these systems smarter, more adaptable, less reliant on us humans to handhold them.
Well, that's the goal of AI, right? Build systems that learn and think for themselves, just like we do.
Well said. And we're definitely making progress, one step at a time. Speaking of which, I think it's time to shift gears and talk about speech. I'm really fascinated by the idea of computers understanding and even generating human sounds. Feels almost magical, you know?
It does have a certain magic to it, yeah. But like any magic trick, there are principles behind it. And that's where phonetics comes in. It's the study of the sounds of speech. How we make them, how we hear them, how we represent them with symbols.
Okay, so if I'm getting this right, phonetics is like the foundation of spoken language. Like letters are the building blocks of written language, and these sounds are the building blocks of spoken language.
Exactly. Just as we use letters to build written words, we use phones, the individual sounds of speech, to build spoken words. Phonetics gives us a way to describe and categorize these sounds so we can analyze all the subtle details of spoken language.
So just like we have the alphabet for letters, is there a special alphabet for these spoken sounds, a phonetic alphabet?
There is. It's called the International Phonetic Alphabet, or IPA. It's a standardized system of symbols that represents pretty much every sound that humans can make in any language.
That's amazing. So with the IPA, we could write down the sounds of any language in the world, even if they have a completely different writing system.
That's the idea. It's a super valuable tool for linguists, speech therapists, anyone who needs to accurately represent spoken sounds.
I can see how this connects to speech processing. If we can represent sounds with symbols, then we can start teaching computers to understand them and maybe even generate them.
You're right on the money. But while the IPA is amazing, it can be a bit much for computers to handle. So for speech processing, we often use a simplified phonetic alphabet called the ARPABET.
So the ARPABET is like a special version of the IPA that's specifically designed for English.
Pretty much, it uses regular ASCII characters to represent the most common sounds in American English. Makes it a lot easier for computers to work with.
Makes sense. Efficiency is key when you're dealing with tons of data. But let's get back to the sounds themselves. I'm curious about how we actually make these sounds. What's going on in our mouths and throats when we speak?
Ah, that's where articulatory phonetics comes in. It studies how we use our vocal organs, our tongue, lips, teeth, vocal cords, to create all those different speech sounds.
So it's like a biological orchestra with all these different parts working together to create this symphony of sounds.
I like that. And just like an orchestra needs every musician to play their part perfectly, we need to coordinate all these articulators precisely to produce clear speech.
I bet. I can imagine that even a tiny change in tongue position could completely change the sound you make.
You're absolutely right. That's why understanding articulatory phonetics is so important for both analyzing and synthesizing speech.
Mm-hmm.
For example, if we want to build a speech recognition system that can accurately transcribe words, we need to know exactly how the tongue moves to produce different vowel sounds.
So by understanding the mechanics of speech production, we can teach computers to recognize and interpret the sounds we make.
Precisely. And this knowledge is just as important for speech synthesis, where the goal is to create artificial speech that sounds natural and fluid, just like a human speaking.
This is so cool. It feels like phonetics is the bridge between the physical world of sound waves and the abstract world of language.
It's a good metaphor. Phonetics is like a translator, helping us decode the secrets of spoken language and build machines that can communicate with us in our own language.
Well said. But before we jump too far into the computational side of things, I want to go back to something you mentioned earlier. The difference between phones and phones. They sound similar, but I feel like there's a subtle distinction there.
You're picking up on something important. Phones, remember, are the actual sounds of speech. Phones are a bit more abstract. They're like the mental categories of sounds, the basic building blocks of a language's sound system.
Okay, I think I'm starting to get it. So a phone is the actual sound we make, and a foam is more like the idea of that sound, the category it belongs to.
You nailed it. Think of it this way. A foam is like a family, and the phones are the individual members of that family. For example, the phone T in English can be pronounced in a few different ways depending on the sounds around it and the speaker's accent.
So the T in top might sound a little different from the T in stop, but they're both part of the same foam family, the T family.
Exactly. The T in top is aspirated, meaning there's a puff of air after it. The T in stop is unaspirated. They're different phones, but they're both allophones of the same foam, T.
Allophones. That's a new one. So allophones are like the different flavors of a foam, the subtle variations that don't actually change the meaning.
Perfect analogy. And these allophonic variations can be pretty important. In some languages, the difference between an aspirated and unaspirated T can actually change the meaning of a word.
Wow, that's wild. So being able to tell the difference between phonemes and allophones is crucial for understanding speech, especially when you're dealing with different accents and languages.
Absolutely. It's a fundamental concept in phonetics and a key challenge in speech processing.
This is making me realize just how complex speech really is. All these subtle variations and nuances happening all the time, and we don't even think about it.
Exactly. And that's what makes speech processing such a fascinating and challenging field.
For sure. But I'm wondering, how do we represent all these subtle variations in a computer system? It seems like we need more than just phonetic symbols to capture all these nuances.
That's where phonetic features come in. They're basically a set of binary values that describe the articulatory properties of a sound. They give us a much more detailed picture than just the phonetic symbol alone.
So instead of just saying this is a tight sound, we can say this is a tight sound that is voiceless, alveolar, and aspirated.
You got it. And by combining these features, we can create a really detailed acoustic fingerprint for each sound.
So it's like each sound has its own unique fingerprint based on how it's produced.
A great way to think about it. And we can use these fingerprints to compare and classify sounds, identify patterns, and even model how sounds influence each other when we speak.
Hold on, you just used a new term. What's co-articulation?
Co-articulation is how sounds change when they're next to each other. Like the N in 10th is influenced by the money sound that comes after it. It makes the N sound more dental with the tongue touching the teeth.
Ah, so co-articulation is like one sound bumping into the next one and changing its shape a little bit.
That's a great way to visualize it.
Mm-hmm.
And we can capture and model these subtle shifts using phonetic features. It helps us build more accurate and robust speech processing systems.
This is incredible. It's like we're taking speech apart atom by atom to understand how it all works.
It's a fascinating process, and a deep understanding of phonetics is essential if we want to tackle things like speech recognition, synthesis, all the different areas of speech processing.
Totally agree. But I think we've covered a lot of ground in this segment. Maybe it's a good time to pause for a second and let everyone digest all this information.
Sounds good to me. A little recap never hurts.
All right, so to recap, we started by jumping into the world of phonetics, which is all about the sounds of human speech.
We learned about the IPA, the International Phonetic Alphabet, which gives us a standardized way to represent all the amazing sounds in languages all over the world.
We talked about articulatory phonetics and how our vocal organs work together like a finely tuned orchestra to produce those sounds.
We also unpacked the difference between phones and foams. Remember, phones are the actual sounds, and phones are those abstract categories that represent the building blocks of a language's sound system.
And we learned about allophones, those different flavors of a foam, the subtle variations that don't change the meaning of a word, but add all this richness and complexity to spoken language.
And finally, we explored phonetic features. They give us a more precise and detailed way to represent sounds by describing their articulatory properties, like voicing, place of articulation, and manner of articulation.
It's been a wild ride through the sonic world of speech, and we've only just scratched the surface. We'll continue our deep dive into speech and language processing after the break, and we'll see how we can use all this knowledge to build systems that can really understand and generate human speech. All right, we're back. It's been quite a journey so far, exploring this world of speech and language processing. We've broken down words, looked at all those hidden grammatical structures, even jumped into phonetics. Lots of cool stuff.
Tons to cover, but we're not done yet. Now, I want to see if we can connect those sound waves, those wiggly lines we talked about, to the digital world, the computer world.
That sounds like a pretty big leap. How do we go from those analog waves to something a computer can actually work with, something digital?
It's all about digitization. Taking that continuous sound wave and converting it into a format that computers can understand. It's kind of like, imagine you have a continuous stream of water, right? And you divide it up into individual buckets. Each bucket represents a little snapshot of the sound's intensity.
So we're basically simplifying those complex waves into something more manageable, something a computer can actually process.
You got it. But how do we actually see what's going on in those digital buckets? That's where spectrograms come in.
Spectrograms, yeah, I've heard of those,
Sure.
but I've never really understood how to read them. What are they actually showing us?
Think of it as a musical score, but for speech. It's a visual representation of all the different frequencies in the sound and how they change over time. You could even picture it like a piano keyboard laid out horizontally, with the darkness or brightness showing how strong each frequency is at a particular moment.
Okay, so, like, if I see a bright spot on the spectrogram around 440 hertz, that means there's a strong A4 note happening at that exact moment. That's pretty cool. But how does this help us with speech processing, with building systems that understand and generate speech?
So speech processing has two main branches: speech synthesis, where we create artificial speech from text, and speech recognition, where we try to turn spoken language into text. Both of these rely heavily on understanding those acoustic patterns that we see in the spectrograms.
So with speech synthesis, we're basically giving a computer a script and saying, okay, perform this for me.
Right, but it's not that easy, of course.
Right.
English especially is full of weird spellings and unpredictable pronunciations. Words like though, through, and tough. How do you teach a computer to pronounce those?
Yeah, even native speakers mess those up sometimes.
We use dictionaries, obviously, but also all these clever rules to figure out the pronunciation. It's like a detective story, where you have to put together the clues to get the right sounds. And once we have the phonetic representation, we can use speech synthesis engines to actually generate the sound waves that match those sounds.
So it's not just about saying the words, it's about saying them in a way that sounds natural, right? Like a real person.
Exactly. Modern systems use techniques like concatenative synthesis, which basically means stitching together little pre-recorded snippets of real speech. Makes it sound way more human and less robotic. And we also have to pay attention to things like intonation, rhythm, stress, all that stuff that makes speech sound expressive and interesting.
Right. It's the difference between a boring robot voice and a voice that you could actually listen to for hours. Okay, but let's flip it around. What about speech recognition? How do we get computers to understand what we're saying?
So speech recognition, also called automatic speech recognition or ASR, it analyzes the acoustic signal of speech, tries to pick out individual sounds, and then figure out which words those sounds represent. We extract all these features from the sound, kind of like we're analyzing fingerprints to figure out what makes each sound unique. The next big breakthrough.
That's a great note to end on. To all our listeners out there, thanks for joining us on this deep dive into speech and language processing. It's a fascinating field, and we've only just begun to explore the possibilities. Until next time.